see who's here. Ahmad Amirul, are you here? Ahmad Amirul still not here. Oh, Ahmad Amirul is here. Okay. Ahmad Imran.
Yes, sir.
Imran is here. Okay. Ahmad Zuhdi. Still not here. Aini Ashikin.
Me.
Okay, we're there. Amirul Hafiz. Still not here. Farhana Emiri. Still not here. Fatin Farha. Okay. Fatin Izzati.
Yes, sir.
Yes, okay. Ilya Danisha. Ilya, still not here. Khairul Nurliana. Still not here. Lukman Hakim. Not here. Maisarah Shafika. Still not here. Muhammad Nazri. Not here. Muhammad Amirul Rashid. Not here. Muhammad Yushaiman.
Yes, sir.
Okay, you're there. Muhammad Firdaus.
Yes, sir.
Yes, you're there. Okay. Muhammad Shafiq.
Yes, sir.
Okay, you're there. Muhammad Afiq Ikhwan.
Yes, sir.
Yeah, okay, good. Then Muhammad Aiman. Muhammad Aiman, still not here. Muhammad Akmal.
I did, sir.
Okay, Muhammad Akmal is there. Then Muhammad Basit. I thought I saw you in here. Muhammad Basit.
Yes, sir.
Okay, there you are. Okay. Muhammad Farid Rizkin.
Ada, sir.
Okay, good. Muhammad Haikal. Still not here. Muhammad ada Muhammad Haikal is here. Okay. Muhammad Harith Irfan. Harith Irfan not here. Muhammad Hazim. Okay, good. Hazim. Just a second. Okay. Muhammad Shakir. Looking. Not there. Nur Irene Nabila. Okay, Nur Irene is there. Nur Azima.
Ada, sir.
Okay, Nur Azima is there. Nur Diana.
Ada, sir.
Okay, you're there. And Zulfakri. Zulfakri is still not here. Again, one more time. Ahmad Zudi. Still not here. Amirul Hafiz. Not here. Farhana Emiri. Not here. Fatin Farha. Not here. Ilya Danisha. Thought you just joined. Ilya, you there? Okay. And Khairul Nurliana. Not here. Lukman Hakim. Still not here. Maisarah Shafika. Still not here. Okay. Muhammad Nazri. Muhammad Amirul Rashid. Then who else do we have? Muhammad Aiman. Still not here. Muhammad Harith Irfan. Not here. Muhammad Shakir. Okay. And Zulfakri. No problem. Oh, who's that? Nur Irene Nabila. Nur Irene Nabila.
Sorry, sir, tertekan.
No, okay, that's it. Oh, all right. Okay, all right then. So let us start the class. I've looked at your answers. Most of you got it right. Yeah. But there are something that I wonder, because there are certain techniques that I didn't show you how to do in class, but it was shown in the answer script. So maybe a different lecturer is the one providing the lecture notes, but I didn't show you the way it's supposed to be done that way. I didn't say it's wrong, but if you're in my class, please follow the way that I show you how to do it, because if not, then you might not understand how the lecturer is doing things. Okay, so let us start with the tutorial. Let me see. Let me present. Please have your answer script ready. But for the second part, some of you couldn't do the second part. Right. Can you see my screen? Can you see my screen? Is it clear? Good. All right. Have your answer script next to you. So problem says the impeller of a centrifugal pump has the following specs. So we have the design flow rate Q. We have the design speed, but you must convert this to radians per second because it's in RPM. How do you convert to RPM, to radians per second? The last bit. Anyone?
Times 2 pi over 60.
Yeah, it's times 2 pi over 60, is it? 2 pi over 60. Is that correct? Anyway. Then we have the impeller outlet diameter D2. Then we have the impeller outlet width P2. Outlet blade angle beta 2 is given. So we have the items. Now we need to assume the inlet flow to the pump is radial. So we need to find the pump head. So pump head is HB. That's the first part. Second part, if you are to install two identical pumps with the above specs in a water supply system that requires a head of 60 meters, flow rate of 0.5 cubic meters per second, we need to determine the arrangement of the pumps to meet the supply system requirements. So this is the second part. So let's look at the first part. We need to find the pump head. So ready? Done? Can go to the next slide.
Yes, sir.
Okay. So I show how to draw the velocity triangles. So we need to draw the pump. So the pump looks something like this. Right. This is the center of the pump. Then we need to draw a radial line straight upwards. And then we draw one of the blades. Okay. So we draw one of the blades as such. So this is the second radial line. So here, closest to the center, this is location 1. And furthest from the center, this is location 2. Right, so this is the blade. The pump is rotating clockwise in this direction with a rotation rate omega. Is my drawing too small? Just nice, can you see it? Is it clear, the drawing?
Just nice, sir.
Okay, good. But I don't like my line. My line is not nice. Draw it again. So it must be a radial line like this. But because I'm using a pen, let me try again. Because drawing on the tablet doesn't look so good. That's better. So this is my radial line as such. So simply I don't like this. Okay, so the pump is rotating in the clockwise direction, rotation rate omega in radians per second. Now, this is how I show us how it's done. So what happens is, I remove, you already know location 1 and location 2. Water will be flowing from the center in this direction, and water will be following the curve of the blade as such. And at this location, the water will just shoot out. If the pump is not rotating, if the blade is not rotating, this is the direction of the water that's going to come out. Right? So what you need to do is you need to draw a tangent line perpendicular to the radial line. So this is your tangent line, right? And therefore, this water coming on this direction, it has a magnitude and velocity, and we call the velocity V2 relative. With me so far? Clear?
Yes, sir.
Good. If the pump is not rotating, this is where the water is going to come out. But the pump is rotating, and when it rotates, it will develop a tangential velocity. So this is the blade punya tangential velocity. And we call this tangential velocity omega R2. Okay, so far? I'll make it longer. Oh. This is omega R2. Right. Clear? Right. So the pump is rotating, and this is the tangential velocity of the blade, omega R2. And if the blade is not rotating, this is the direction of the water coming out. But since the blade is rotating, we need to know where is the water coming out from the pump. So what we do is we need to draw a parallelogram. So this is the tangent line. So you draw a parallelogram as such. And then you draw this other line. Let me see. Is it correct? Okay, somewhere here. See, that's your parallelogram. Because this is also omega R2, and this velocity is also V2 relative. With me so far? Okay. So where is the pump pushing the water? So this is where the absolute velocity, this is the magnitude and direction of the water coming out. And this we call the absolute velocity V2. So this is what we have. Clear? This is how we obtain the absolute velocity V2. This is where the water is coming out from the pump. That's the magnitude, because we're looking at velocity vectors. Clear? Done? Okay. Now, the angle that the relative velocity V2R makes with the tangent line, we call it the angle theta 2. And the angle that the absolute velocity V2 makes with the radial line, we call this angle alpha 2. Okay? Good. If this is the angle beta 2 at this location, this is also angle beta 2. Right? And we can also break down this absolute velocity V2 into its normal velocity component, which is this one. This is V2 normal, and also into its tangential velocity component. This is what we call V2t. So if this is V2n, this is also V2 normal. And this component right here is V2T. If this is V2T, then this component here is also V2T. Everybody see that? Clear? Good. Now we need to know this last component. If this green arrow is omega R2, this purple arrow is V2T, what is this? This length here. What is that? This length here. Anybody? The green arrow, the length is omega R2. The purple arrow, the length is V2T. So what is this length kat sini?
Omega R2 minus V2T.
Omega R2 minus V2T. Right. So now we can have a relationship between the angle beta 2, omega R2 V2T, and V2N. And that relationship is tangent beta 2 is equals to omega, no omega, it is V2N over omega R2 minus V2T. Correct? Agree with me?
Yes, sir.
Yeah. Good. Then the other relationship I can have is with the angle alpha 2 with V2N and V2T. And the relationship is tangent alpha 2 is equals to, in this case, it is V2T over V2N, correct? Yes. So this is how we obtain the relationship. Because I saw some work being done, because this is my blade. My blade is in this direction. The palm is rotating clockwise. I saw some answers showing me something. I don't know how it's shown. This is the triangle cut. So this I didn't show you how to do. Please do not use this method. I don't say it's incorrect, but it's probably from different lecturer when explaining it. So don't use this method. Use the way that I show you, because I do not memorize the formulas. You just have to draw the triangle and then you can have the relationship, right? So from here, let's go back to the problem. Now the problem says that we are given the flow rate. We are given the flow rate, Q. We are given the design speed, omega. We are given the outlet diameter D2. We are given the blade width B2. We're given the blade angle beta 2. All these are given. We're supposed to find HP, the pump head. Now, what else did they tell? They say assume the inlet flow to the pump is radial. Oh, inlet flow to the pump is radial. So let me see. Therefore, this is what we have. The inlet flow to the pump is in a radial direction. What does that tell me? So this is in radial. What is the angle alpha 1 kat sini? Is there an angle alpha 1 kalau flow is radial in that direction? Anyone? Do you see? Look at location 2. So if this is radial, what does that mean? That means this is absolute velocity V1. Nampak? This is V2. So ada angle alpha 1 or not? Is there an angle alpha 1? Any guesses? Ada tak?
90 or 0.
So if you look at this, nampak? If V2, absolute V2 is moving towards the radial line, this is a radial line, what happens to angle alpha 2? It gets smaller and smaller, right? Sampai to the radial line, alpha 2 will become 0. So therefore, kalau we look at location 1, if the flow is in a radial direction, in this case, then angle alpha 1 is 0. With me so far? Clear? Nampak? Because this is absolute velocity V1. Straight up. Everybody clear or not? Okay. Look at absolute velocity V2 kat sini. Nampak tak? This one. Absolute velocity V2. Do you see it? Okay. If absolute velocity, you move it closer to the radial line, what becomes of angle alpha 2? Makin kecil kan? Kalau you pergi to sini, V2 rotate counterclockwise, what happens to angle alpha 2? Makin kecil kan? Yes. If absolute velocity V2 is right at the radial line, what happens to the angle alpha 2? Kalau kat sini adalah V2 je kat sini. This is, let's say, V2 is here. What happens to the angle alpha 2? Exactly, right. So this, kalau dia keluar dekat sini, then alpha 2 is 0. Agree? Yes. So look at location 1. Absolute velocity V1 is right along the radial line. Is there an angle alpha 1? Ada tak? Alpha 1 tak ada. Because macam cakap, kalau this is location V2 kat sini, you ada angle alpha 2, isn't it? If location V2 is dekat sini, nampak dekat sini, ada angle alpha 2 tak? Yeah, exactly. So similarly kat sini, so this is absolute velocity V1 along the radial line. So ada angle alpha 1 tak? Do you see that right? Everyone see that? Everybody clear with that?
Clear, sir.
Okay, tak clear cakap. So if you're clear, now, therefore, what is absolute velocity V1? It is equal to the normal component V1n. And what happens to the tangential velocity V1 for song? Right. With me so far? There is no V1 tangential component dekat sini because the flow is moving outwards in the radial direction along the radial line. So tak ada tangential velocity component. So compare dengan location 2. Ada tangential velocity component tak V2T? Ada kan? Because absolute velocity V2 is in this direction. Tapi kalau absolute velocity is along the radial line, nampak? There's no V2T. Do you see that, guys? Clear? Confused? Okay.
Okay, sir. Clear.
Okay. Yang lain tu okay tak? Ikut je. Silence mean understand. Okay, so one person say clear, then that's fine. So this is what we have, right? So we're supposed to find the pump head. Done? I can go to the next slide.
Yes, sir.
Okay, good. So next slide, we have a relationship with pump efficiency. Pump efficiency, eta pump, is equals to the water horsepower over the brake horsepower. What is the water horsepower? It is rho G Q pump hit. What is the brake horsepower? It is omega multiplied with the shaft torque. It is omega rho Q, then it is R2 P2T minus R1 P1 T. Okay, not?
Okay, sir.
Yes. If we were to assume 100% efficiency, but before that, I can cancel the terms. Nampak? I can cancel density. I can cancel Q. If I assume 100% efficiency, then this efficiency is 1. So therefore, what do I have left? GHE over omega R2 P2T minus R1 P1T. Okay, so far? Apa tak? Kalau 100% efficiency, this eta value is 1. Betul tak?
Yes, sir.
Okay. Kalau I assume 70% efficiency, eta ni berapa?
0.7.
It is 0.7. Okay, so when you're working with pumps, for this problem, we assume 100% efficiency, so we can use 1 regards to. Tapi kalau dia kata the pump is 70% efficiency, it is not 1, it is 0.7. In this case, we are fine because kita assume 100% efficiency. So, can I move to the next slide?
Yes, sir.
Okay, so what we have then is we have the relationship of the pump head is equal to omega over G R2 P2T minus R1 P1T. Okay, so far? Is that correct?
Right, sir.
Okay. We know that the tangential velocity V1 is 0. Right. So what we are left with is just omega over G R2 P2T. Right. And therefore, we know omega, we know gravity, we know radius R2, we do not know V2 tangential. Okay, so far?
Okay, sir.
Done. Done? So this is what we need to look for to get the pump head. We need to know what V2T is. Done?
Yes, sir.
Okay, done. Not done, let me know. Done. So therefore, to find V2T, we know that the flow rate is equals to 2 pi R2 B2 V2 normal. So therefore, we can find V2 normal is equals to Q over 2 pi R2 V2. And then we substitute with values. This flow rate I obtain 0.2. This I get 2 pi times, what is the radius, is 150 times 10 to the power of -3. What is the width? It is 30 times 10 to the power of -3. So I can turn this up. What value do you obtain? Anybody got a value that you obtain from your answer script? What do you get?
7.074.
Exactly, 7.074 unit in meters per second. Anybody got similar values? Similar values?
Similar there.
Okay. All right. Done?
Yes, sir.
Okay, done. Done, let me know. Why am I finding the normal velocity? Because I have a relationship here. I know that the tangent beta 2 is equals to V2n over omega R2 minus V2 tangential. I know all these items. Now I know what V2n is. I can find V2t. So therefore, V2t is equal to omega R2 minus minus the V minus V2 V2n over tangent beta 2. And I substitute the values. I got the rotational speed omega to be 209.44 multiplied with the radius R2 is 0.3 over 2 minus V2n was 7.074 divided by the angle tangent 20 degrees. What value do you obtain from your work, those have done up to this point?
11.98.
Yes, 11.98 unit must show meters per second. Yeah, show the units. Anybody got similar values? Similar values? And check. Okay, that's good. Done? Not done?
Okay, done.
Done? Not done, let me know. So done, I move to the last slide. Not last slide, next slide. So you can see, I know the tangential velocity now. And therefore, I know I can find the pump head, which is omega over g. And it's just now R2 V2t. I can just write down minus R1 V1t, where tangential velocity here is 0. So therefore, I can substitute with the values. This is 209. For gravity, use 9.81. Do not use 10. And what about R2? It is 0.15. Plus the tangential velocity was 11.98. So what do you get for the head? Those who've done to this point.
$37.
38.37. Must put the unit. Must be in meters. Everybody got similar values?
Almost same.
Almost same is fine. Yeah, 38.3, 38.4, that issue. So we have solved for it. Any questions so far for the first part? Clear or not?
Clear, sir.
Easy or not? Not easy? Easy? Right? Done?
Done, sir.
Okay, not done, let me know. So done. Let's go and look at the second part. Second part, kat sini. All right. So here we know that the Q for this pump is 0.2 cubic meters per second. And we already found the head, which was 38. Oh, what happened to my pen? Hold on. 38. Let me write 3. 38.37 meters. Now, second part. If you are to install 2 identical pumps with the above specs in a water supply system, that requires a head. So that requires a head of 60 meters. So system requires a head of 60 meters and a flow rate of 0.15 cubic meters per second. Determine the arrangement of the pumps to meet the supply system requirement. Now, this is the pump for, this is the spec for one pump. Tell me, does one pump meet the system requirement? Kalau one pump in terms of flow rate? This flow rate 0.2, does it meet the system requirement? Look at it again. The pump can supply 0.2 cubic meters per second. The system requires 0.15 cubic meters per second. Does it meet the flow rate requirement?
Yes, more than enough.
Yes, this is one pump though. One pump. It meets the flow rate requirement. But look at the head that the pump can supply. The pump can supply a head of 38.37 meters, but the system requires 60 meters. So does it meet the head requirement? Yes or no?
Not enough.
Not enough head, isn't it? So this is the system. The system needs to bring the head up to 60 meters. But this one pump only brings the head to 38.37. You see what I'm trying to show you? Nampak tak? The pump nak bawa air up 60. Bukan, the system needs a head of 60 meters because the location is dekat sini. But the pump can only supply up to 38.37. Boleh tak? Do you see that? You cannot push the water up 60 meters. You can only push the water up 38.37. This is what it means by head. Follow? Nampak kan? See? So one pump is not enough. So that's why this is a give me problem. Dia kata install 2 identical pumps dah. Oh wow, so easy this problem. Because the guy already know that one pump cannot supply the head, but can supply the flow rate. So now you need to install 2 pumps, but we have to find the arrangement. What type of arrangement can we install it? We can install it either in series or in parallel. Betul tak?
Betul, sir.
Yes. So with that, everybody clear with the second part? Nampak tak what we're trying to look at? Not clear, ask me now. Because your second assignment will be on fluid machinery. Any questions? Clear with this?
Okay, clear.
Okay, clear. Done. I can get to work. Okay, I go. Done, Ruben?
Yes, sir.
Good. So, therefore, I will write down one pump can supply a heat, a flow rate of 0.2 cubic meters per second, and can supply a heat of berapa? 38 point, berapa tadi? 38 point, what was the answer that we got? 38.37. 37 meters. So now we draw a table as such. So I will second, oops. Okay. I will split into 1, let's see, 2, 3, and 4. So kat sini ada column, ada row, another row. All right, so this is the system requirement. In terms of heat, unit is meters. In terms of flow rate, in cubic meters per second. So the system requires a heat of 60 meters and a flow rate of 0.15 cubic meters per second. If we're to install 2 pumps in series, what is the heat provided by 2 pumps in series? Kalau one pump provide a flow rate of 0.2, heat of 38.37. 2 pumps in series, what is the heat provided by this pump? Anyone?
Times 2 ke, sir?
Yes. For 2 pumps in series, it is double the heat, right?
76.70.
38.37 times 2. So I got berapa? 70?
76.74
7?
meter. 4.
74 meters. Yes. 2 pumps in series will double the heat. What about the flow rate? What is the flow rate if you install 2 pumps in series? Anyone? Flow rate for 2 pumps in series.
0.2.
It is still the same kan? The flow rate doesn't change. Clear so far? The flow rate doesn't change. Clear? Questions?
Dia tak berubah sebab dah memang cukup rasa.
That is the nature if you install 2 pumps in series. If you install 2 pumps in series macam ni. From the notes and recordings, the head will double. Kalau series macam tu, the flow rate is macam this direction. It will double the head, tapi the flow rate tak berubah. Still 0.2. Sama macam satu pump. Clear? Nampak tak? This is a series arrangement. Yes. If you were to install 2 pumps in parallel. So bermakna air itu masuk dan we install the pump like this. Right. What happens to the head? Will it be the same? Will it be double? It'll still be the same, isn't it? So it is still 38.37 meters. But what about the flow rate? Will it be the same? Or double?
Double.
It'll be double, isn't it? It's 0.2 times 2. Berapa? 0.4. Nampak tak? Two pumps in parallel, the head is the same, but the flow rate is double. Done?
Done, sir.
Now we have to select. So we have to look at our results. We have 2 pumps in series and 2 pumps in parallel. Let's look at the 2 pumps in series. The system requires 60 meters of head. The 2 pumps in series provide 76.74. Does it meet the system requirement? Yes or no? Does it meet or exceed the system requirement? Yes or no? Anyone? Does it meet or exceed the system requirement? It meets and exceeds the system requirements. The system requires 60 meters only of head. But the 2 pumps in series can provide 76.74, which is more than the system requires, so we're good. The system requires 0.15 cubic meters per second flow rate. The 2 pumps in series can provide 0.2 cubic meters per second. Does it meet or exceed the system requirement? Yes or no?
Lebih.
So does it meet the requirements?
Yes.
Yes. Look at 2 pumps in parallel. System requires 60 meters of head. 2 pumps in parallel providing 38.37 meters. Does it meet the system requirement?
No, not enough.
No. System requires 0.15 cubic meters per second flow rate. The pump in parallel provide 0.4 cubic meters per second. Does it meet the system requirements?
Yes. Yes.
Now, if I have to choose, which one do I choose? In series or in parallel?
Series.
Series.
Yes, because it meets all the requirements. Yang parallel does not meet one requirement, so we cannot install. But this is not the answer. The answer is you have what? Apa nak masuk? Okay. All right. So we are looking at the question, determine the arrangement of the pumps to meet the supply system requirements. So we have to write down. So arrange, okay. Let me see what dia kata tu. So arrange the 2 pumps in series as it meets as it meets the system requirements. So that is the answer that you have to put down. Arrange the two pumps in series that it meets the system requirements. Clear, guys?
Yes, sir.
Questions so far? All right. Done? And go to the next slide.
Done, sir.
Okay. So therefore, if you recall, whenever you're looking at pumps and system, we have the flow rate and we have the head, right? So your system, kalau you need to bring water to this level, for example, so dia ada dia punya head ni, dia punya height, dia ada height dia berapa meter kan? So this will be your height that your system requires. So that is the static head. Just to bring up to that level. But if you want the water to flow, as you increase the flow rate, you will need to increase the head. The more flow rate you want, the more head you require. So this is called your system curve. With me so far? Clear with that?
Yes, sir.
And you have to select a pump that will be able to supply the water to the system. So you take the pump and you plot the pump performance curve kat sini. Let me draw properly. So mana color dia? So draw the pump curve. So this is the pump performance curve. Right. And where the two lines intersect, kat sini, this will be its operating point, and this will be the flow rate at the operating point, and this will be the head at the operating point. See that? Nampak?
Nampak, sir.
Yes. So this is all there is in this fluid machinery. We have pumps and turbines. So for this problem, we're just looking at the pump punya performance. But this one is when we are checking to see whether the pump can provide the water supply or any liquid supply to the system. So this is how it's done. Any questions so far? Because we are done with topic 4, and then I will give you the assignment in topic 4, on topic 4, the second assignment, also group assignment. Are we done? Clear?
Sir,
Yes?
dia punya curve tu memang semua macam tu ke?
It looks like that, but sometimes it looks like in the taco, but how it looks like does not matter. But normally it looks something like this, but if you look in your textbook, the curve doesn't look like that, isn't it? So you have to plot it. What is important is you're able to plot the system curve and the pump curve. Boleh?
Okay, sir.
Okay. So therefore, any other questions before we on this problem? Dah selesai? Done? Okay. Okay, so I start presenting. Now, What I must say, I've already posted the notes to topic 5, which is compressible flow. Then I will give you the tutorial assignment for topic 5, maybe next week. And also the assignment on assignment 2 will be a group assignment. Here's what I want to tell you. All right, when is your submission for assignment 1? Today, is it? Due date?
Yes, sir.
Yes. So yes, it is a group assignment. If it's a group assignment, that means I expect all team members to be contributing to the group assignment. If you feel that one of your team member is not contributing or whatnot, and you feel that he or she does not deserve to get the grade, so when you submit the assignment, you don't have to put his or her name on the front cover, but you must inform me the reason why you do not do that, right? Because it has been done before. Either one team member did not do any work whatsoever, even though have already been asked by the other team members. So they decided not to put his or her name on the front cover, and therefore that person did not get any grade for the assignment. So, but I suggest that all team members should contribute to the assignments. The second assignment will also be a group assignment. So clear with that, guys, as a team?
Yes, sir.
Okay.